Alright, we're going to look at how to determine the quantity of heat released while converting steam to ice. So because this problem discusses steam and ice in the same problem, two different phases of a substance, this is going to be a problem that requires a graph. That's how you're going to know you need to use a graph, because two different phases of matter are going to be discussed in the same problem. Like all problems, we want to identify what we know and keep a good order of everything we know. How many calories? So that's our question mark. That means we're going to solve for heat. Calories is heat. Are released when 125 grams of steam, so that's a mass, at 120 degrees C, so that's a first temperature, are cooled to ice at -15. So here's two temperatures that we're going to need. Convert your answer to kilocalories and then also kilojoules. So we need to ID our variables to start. And the only variable that we can really easily ID right now is going to be M, and that is 125 grams. Because this substance is water, we know some other facts about it, like the specific heat capacity of water, liquid water, but also for ice and steam, which are also numbers that you just need to have memorized. Because it's a problem that has converting from steam to ice, and it's going to be two different phases of matter, we need to draw a phase change graph to help us keep track of all of our variables. When we do that, you're going to want to put in your 2 points to your temperatures that are given to you as your initial and your final. This graph doesn't have to be to scale, this is just to keep us organized. So the 120 and the -15 are both included. So this is the starting and stopping points. Then I need to think to myself, are there any important temperatures for water in between those two values? And there are. 100 is the boiling point or condensing point of water, and then 0 is the freezing point or melting point of water. Since we're cooling, our graph is going to go this direction. It's going to have a negative slope. So I'm going to put a flat part of my graph at both the melting point, freezing point, and then the boiling point, condensing point. During those phase changes, you need to know that there's going to be a flat part of your graph. Then connect your graph starting temperature to your plateau, connect your two plateaus, and then your plateau to the final temperature. Label these parts of your graph. There's going to be 5 parts. Whenever we have a graph like this, there's going to be 3, 4, 5. There's going to be an odd number of parts whenever we have these graphs. You want to do your delta t's for each diagonal portion of the graph. Remember, diagonal portion is showing a change in temperature. So delta t for phase 1 is going to be 120 minus 100, so that's 20 degrees C. And delta t for phase 3 is going to be 100, because 100 minus 0. And then finally, delta t for phase 5 is going to be 15 degrees difference. So label your delta t's. You could also do your C values for the diagonal portions of your graph. C at steam is 0.49. C at liquid water is 1. C at ice is 0.49 as well. Then since we have 5 parts, we're going to have to plug those all in. So plug in your values to your equations. I like to label each of my portions of work. So part 1, all of these are delta H. They're all going to have the mass. So go ahead and throw the mass in, which is 125. Heat is an extensive property based on sample size, so mass is important for all of these. And then 1, 3, and 5 are going to have the specific heat. So 1 is 0.49. 3 is value 1, because that's liquid water. And then at ice, 0.49. These specific heat capacities are specific to the phase of matter. And then your delta T's, we did 20 for phase 1, For phase 3, we did 100. And then for phase 5, we did 15. So phases 2 and 4 then are going to be multiplied by the constant value for the heat of fusion, heat, and vaporization. So 2, since this is the boiling point, condensing point, that's going to be the heat of vaporization. That's the heat that's either released or absorbed when you're going from a gas to a liquid, going from a vapor to a liquid. And that's 540. So you need to have that number memorized. And then down at the bottom for phase 4, when you're going from a liquid to a solid, when you're fusing your liquid particles together to make a solid substance, that's going to be 80. Through all this, I'm clearly omitting all my labels, but if you were to include the labels, they would cross off and give you the appropriate ending unit, which in all cases would be calories, because we're solving for heat. The numbers that you get are 1225, and this would be the place value we would keep based on 3 sig figs right here for the 20. The problem number 2 would be 67,500. Place value we would keep would be the 4th one from the 125. Number 3 is 12,500. We would keep this place value because we have 4 sig figs for both temperature and the mass. Part 4 of your graph would be 10,000. We get that from sig figs. We get 4 sig figs from the 125, so that's this 0. And then lastly, part 5 is 918.75. Sig fig we keep there is the 8. We get 3 sig figs from the 15. So why am I marking all of these place values as far as sig figs go? Because now we're going to sum these together. We're going to add them all together. And adding rule is based off of place values, so we had to mark all those place values. If you put that in your calculator and you sum it, you get 92,143.75 calories. But we need to think about sig figs. So sig figs here go to the tens, 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 ones. Of those place values, the tens is one spot further than the ones, so we get to keep to the tens, which means that we have 92,140. So I need to keep this in the tens, fill it with a 0, no decimal point because that would make the wrong number of sig figs. And this is calories. That's the total change in heat for each phase of the graph added together. The problem also asks us to solve for kilocalories and then kilojoules. So kilocalories, you're going to take your answer, 92,140 little c calories. Kilocalories are big C calories, so there's 1,000 little c calories for every 1 big C calorie, which equals 92.14 big C calories. And then doing kilojoules, 92,140 little c calories. You need to know that for every 1 little c calorie, there are 4.18 joules. Calories will cross off. And then for every 1,000 joules, there is 1 kilojoule, just using metric prefixes to make that conversion. Joules will cross off. This math gives you 385.14, but we get 4 sig figs, so 385.1 kilojoules.